Last lesson, we tuned hyperparameters by hand, one guess at a time. That's slow and easy to do badly. Let's hand the search over to the computer. There are two popular ways to do it: grid search and randomized search. Grid search is the straightforward one. For each hyperparameter, you list a few candidate values. Here we're tuning two: the tree depth and the learning rate. 4 choices each. Every combination becomes one cell in a grid, 16 little experiments in total. Now we run cross-validation on every single cell, and write its score inside. Brighter green means a better score. When the grid is full, we simply pick the best cell. Here it's a depth of 6 with a learning rate of 0.1, and we're done. But grid search has a problem. It explodes. 4 values by 4 values is 16 runs. Add a third hyperparameter with 4 values, and it jumps to 64. A fourth, and you're over 200. Worse, the grid spends just as much effort on obviously bad corners as on the promising ones. Randomized search takes a different tack. Instead of a fixed lattice, it samples combinations at random from the ranges you give it. You set a budget, say 12 trials, and it scatters them across the space. With the same budget, random sampling can reach into corners a coarse grid would skip entirely, and often finds a great setting faster. Here's the key insight: side by side. Usually only one hyperparameter really matters much, that's the horizontal axis here. The grid on the left tries just 3 distinct values of it, because its points line up in columns. The random search on the right tries 9 different values of that important parameter. So for the same number of runs, random search explores the dimension that matters far more thoroughly. That's why it's often the better default. So, grid search tries every combination and is simple but explodes. Randomized search samples and usually explores better for the same budget. Both use cross-validation to score, and both leave the test set alone. Now, when a model isn't good enough, how do we know what to fix? A learning curve tells us. That's next.